Okay, so let's go ahead and get started. Good morning, good afternoon, and good evening to all our esteemed customers who are joining us from around the world. Hello, everyone. My name is Lokesh Chara, and I'm one of the managers for the Arista Technical Services team. And on behalf of the entire team, I extend a warm welcome to each and every one of you to this remarkable webinar series graciously hosted by the Arista Technical Services team. For those who are joining us for the first time, please allow me to provide a brief overview of this initiative. Throughout these webinar sessions, Sandhya, if you could move on to the next slide, please. Our primary objective is to foster knowledge sharing with our valued customers, focusing on the comprehensive and the practical topics which are the utmost importance to everyone. A bit about the background. We embarked on this endeavor in 2022, covering essential subjects such as switch health checks, upgrades, and the maintenance planning. And now in 2023, we are thrilled to continue our journey, delving into more advanced technical topics. So if you wish to revisit any of our previous sessions, including the presentation material, they are accessible on our Arista community page. In the 2023 series, we dedicated our first quarter to exploring a typical Layer 2 and Layer 3 setup debugging. And throughout these sessions, we did a deep dive into numerous practical use cases and valuable commands that prove instrumental in troubleshooting such environments. And in Q2 23, we shifted our focus and we moved on to a more complex topic for which we did receive a lot of demand, and that is VxLAN. Recognizing the vastness of this VxLAN topic, we actually carefully structured our webinar series into 3 distinct sessions to provide a comprehensive coverage. In our previous 2 sessions, we focused on the VxLAN bridging and routing setup. And today, in this session, which is a continuation of our last session, we are doing a deep dive into a complex VxLAN environment. So for today's session, we actually created a lab topology based on customer interactions, and we will be navigating through this topology and highlighting the debugging approach. We did send out this topology proactively to our customers on 27th of June, but our speakers will be highlighting this topology in between the debug scenarios. So we highly recommend you to take a snapshot of this topology and keep it up on your screen for reference. We have a PDF download link available in the QA section, which our panelists are putting right now. So please download it and keep it handy during the course of the presentation. Sandhya, could you move on to the next slide, please? Okay, a little bit about the webinar schedule in 23. After today's session, we are actually going to take a short break in July, and we'll be resuming back in August for 3 more sessions, which will be focused on EVPN. The registration link that remains the same, what you have registered for these previous sessions and today's session, and you'll continue to receive notifications on the schedule through the registrations what you already have. So for today's session, we are delighted to have our 2 exceptional engineers who will guide us through this session with their expertise and insight. Firstly, we have Sandhya Mani, who will expertly navigate us through the CLI component to debug the VxLAN routing complex scenarios. And following Sandhya, we will have Vijay Gopal Sriram, who will delve into the CloudVision side of the presentation, showcasing CloudVision's availability, showcasing CloudVision's capability, and demonstrating how it can enhance your VxLAN experience. Again, this session will be recorded and will be made available on the Arista Community Central if you'd like to have access to these recordings in the future. Also, along with the presenters, we have our technical leads as part of the panel who can help answer any questions what you may have during the course of the presentation. So we encourage everyone to use the Q&A manager, what we have available in the Zoom, to ask our panelists any questions what you have during the course of this presentation. So without taking any further time, at this point, I would hand it off to Sandhya for taking you through the CLI part. Sandhya, take it away.
Thank you, Lokesh. Hello, everyone. My name is Sandhya Mani, and I am a technical solutions engineer with Arista Networks, operating out of the Asia-Pacific region. I'll be walking you through how to debug traffic flows in a VxLAN routing environment via the EOS command line. This is a logical extension of the webinar that we had last month on the same topic. The scope of today's presentation is to build upon our existing toolkit of troubleshooting methodologies, as well as CLI and Cloud Vision utilities to isolate and identify problems in typical flood and learn VxLAN environments. The nature of the topology we're going to be using today is similar to that from the last two webinars. This is a pretty straightforward leaf spine architecture. VTEPs 1 and 3 are 7050 SX3s, whereas VTEPs 2A and 2B are 7280 SR2 devices. The spines also belong to the same family, being 7280 CR3s. The spines act as an L3 transit and form the VxLAN underlay. The routing protocol that's being used to disseminate the VxLAN primary loopbacks amongst the VTEPs is eBGP. VTEPs 1, 2A, and 2B are routing VTEPs, whereas VTEP 3 is a bridging VTEP. The routing VTEPs have an SVI for VLANs 10, 20, and thus also have the virtual VTEP or VVTEP configured. In the last webinar, we touched upon the two types of Anycast gateway mechanisms. We'll be covering both in detail today in two unique problem statements. The VLAN to VNI mapping is also going to remain the same for both problem statements. VLAN 10 is mapped to VNI 1010, VLAN 20 to VNI 2020, and the virtual VTEP or VVTEP is 10, 10, 10, 10. So with that, let's dive into problem 1. The problem has been presented as database syncing between storage servers not functioning in the customer's environment. These database syncs occur via SCP or secure copy. Interestingly, this was working for the customer until a couple of hours back, and the customer is unsure of what changes were made recently. These database syncs are failing persistently, and as a sample provided to us, the customer is unable to securely copy a backup file residing on host 2 to host 1. Now, with this particular problem in this topology, the Anycast gateway that is configured on VTEPs 1, 2A, and 2B is the IP address virtual knob, and you would be familiar with this as this configuration is similar from last webinars. Having IP address virtual means that the SVIs on the routing VTEPs will have one IP address only. The topology on the right here also highlights the sample broken flow. So let's go over to the devices to further troubleshoot this. I have hosts 1 and 2 here on the CLI, between which we have a sample broken flow. VTEPs 1, 2A, and 2B are supposed to be the directly connected VTEPs. Let's first confirm the IP addresses configured on these hosts. There's a simple command we can run to do that. The Linux hostname utility with some filtering gives us the primary IP of the host. So host 1 is 20.0.0.2 and host 2 is 10.0.0.1. Now let's go ahead and confirm the customer's issue. I'll also have the topology brought up frequently throughout this presentation to help trace flows. Now, as per the problem statement, we are unable to securely copy a file named host1 server backup that is residing in the flash directory on host 2 to the flash directory on host 1. The command that I'm running right now is SCP, which stands for Secure Copy Protocol. This makes use of the SSH protocol, and SSH typically runs on port 22. We can see that a banner from host 2, that is 10.0.0.1, appears successfully. However, the download initiates and then stalls with absolutely no progress made at 0 kbps. Given that SCP is being used, the first thing to check would be if port 22 is indeed open on host 2. A simple telnet would help us confirm that. All right, host 2 appears to be responding, and this confirms that port 22 is indeed active and listening on host 2. The second thing to do would be a simple ping test with the default size. This appears to be working as well. However, this ping working does not signal that everything is okay with the network. All it tells us is that there is a particular path in the network that is helping establish connectivity between these hosts. There could be multiple ECMP paths in this leaf spine topology, and depending upon the source and destination IPs for an ICMP packet, there is always one path that these packets would take. Now, to further confirm if this is potentially an issue with ECMP, let's try to do multiple trace routes to the destination. With Linux UDP traceroute, while the source and destination IPs are not going to change, the source and destination ports will vary, and that will provide the packets with enough entropy to take different paths if they exist. Now, from the looks of it, all trace routes are succeeding, and we can reasonably say at this point that this may not be an issue with ECMP. So before we proceed, let's get a little familiar with the VxLAN environment for hosts 1 and 2. We know host 1 is directly connected to VTEP 1, and host 2 is dual home to VTEPs 2A and 2B. Let's first run show version to check the platforms in the code here. VTEP 1 is a 7050 SX3, and VTEPs 2A and 2B are 7280 SR2 devices. All these devices are running maintenance code 4.28.3m. And from the LLDP neighbor output, we can now confirm that host 1 is indeed connected to VTEP 1 and host 2 to VTEPs 2A and 2B. Next, to get some VxLAN specific information on these three VTEPs, we can first run show VLAN to check the status of VLANs 10 and 20. We can see these three VTEPs are extending VLANs 10 and 20 across a fabric, since the port VX1 or VxLAN is present in this output. Furthermore, since they have the CPU port also listed here, these three VTEPs should presumably behave as routing VTEPs with an SVI. Next, let's check the VxLAN configurations. From the show interface VxLAN 1 output, we can see that the VLAN to VNI mapping is consistent everywhere. VLAN 10 is mapped to VNI 1010 and VLAN 20 is mapped to VNI 2020. The flood list on these VTEPs is uniform and basically includes all the three VTEP IPs in the environment, along with the VPTEP IP. Now, VTEPs 2A and 2B have the same primary VxLAN loopback since they are in MLAG. And finally, all three VTEPs have a virtual VTEP IP configured, which is 10.10.10.10. Now, this IP can be thought of as a virtual endpoint that owns the gateway for all segments. Next, let's go ahead and check the SVI configurations under VLAN 10 and 20. The Anycast gateway mechanism here is IP address virtual, and we can see the same virtual IP is configured across all three VTEPs per VLAN. The virtual IP for VLAN 10 is 10.0.0.254. The virtual IP for VLAN 20 is 20.0.0.254. And the virtual map configured across all three VTEPs is 1C73AA. Now, with IP address virtual as the chosen gateway mechanism, it's important to note that if we want to test any host's connectivity to the gateway, it's always better to ping the gateway from the host. Pinging the host from the gateway is generally not recommended. And to quickly illustrate this, let's ping 20.0.0.2 from the directly connected VTEP 1. We can see the ping fails. Now let's do the same ping from the connected host, that is, ping the directly connected gateway from the host. This ping succeeds. Now let's take a TCP dump on the host while we're pinging from the gateway. We can see the ICMP request comes with an IP that is not the virtual IP. This is 1001. Let's check where that IP resides on VTEP 1 via show IP interface brief. And it appears to be loopback 1. And this loopback should also be a part of VRF-A that houses VLANs 10 and 20. Now, this is happening because with IP address virtual configured, any pings originating from the SVI will undergo a source network address translation or source NAT. I'm also showing you the same behavior when pinging host 2 from VTEPs 2A and 2B. The way the source NATing is done is via a DMA driver in hardware. The source IP of the ping is NATed to the highest loopback in the VRF if that exists. If such a loopback doesn't exist, the highest interface IP address is chosen. The reason such a source NAT is done is to ensure that the ICMP reply from the host lands on the VTEP that actually originated the ICMP request. Since with IP address virtual, all SVIs across all routing VTEPs have just one IP, which is the virtual IP. To ensure that such pings from the gateway work with IP address virtual configured, the hosts would need to have reachability to these selected IPs. So we can see here from this output that the TCP dump shows the source IP to be the highest loopback configured on btips 2A and 2B. Additionally, there's also a command that we can use to specify this IP address that is to be taken for such traffic originating from the SVI for a specific VRF. Now, this command would override the automatic selection of loopback addresses or interface addresses. The command is as follows: IP address virtual source NAT, and then you specify the VRF, and then you specify the address. So for next steps in troubleshooting the actual problem at hand, getting some visibility into what the hosts are sending and receiving when we initiate the secure copy will help a lot. To save us some time, we captured two PCAPs at host 1 and host 2 while initiating the secure copy. Let's go ahead and take a look at these. So from the capture on host 1, which is on top, we can see the packets 1, 2, and 3 form the TCP three-way handshake. We see the SYN, SYNAC, and ACK. Post this, we continue to see two-way communication between 10.0.0.1 and 20.0.0.2. These packets 4 to 17 appear to be negotiating and exchanging the SSH protocol version and the client-server cryptographic keys. It's also interesting to note that the packet sizes here appear to be quite small, with the largest being close to 1,000 bytes. On Arista, we know that the default IP MTU is around 1,500 bytes. Now, the packet capture on host 2 conveyed the same story, except that when host 2 began sending segments of the file towards host 1, something interesting seems to have happened. So the packet I've highlighted is packet 74, which is the first segment of the file. The sequence number of this packet is 3210, and the acknowledgement number is 2614. Packets 75 to 84 are subsequent breakups of the file. Now we can see packet 75 has sequence number 3210 plus 1448, which is 4658, and the acknowledgement number is the same, which is 2614. There are 10 of these segments with the same acknowledgement number 2614, meaning host 2 was expecting an aggregated or selective acknowledgement for these 10 segments. Then from packet 85, we see TCP retransmits for packet 74, which was the first segment sent out with sequence number 3210 and acknowledgement number 2614. It looks like host 1 never received that first segment, so host 2 is continuously retransmitting it. Again, it's interesting to note that these packet sizes are noticeably bigger, of length around 1514 bytes, with the SCP payload being 1448 bytes. This particular symptom, where bigger sized packets get black-holed, is typical of egress MTU mismatches in the environment. But we would need more data to substantiate this. Since we're dealing with VxLAN, it's always important to remember how packets are encapsulated by the technology. I have this packet capture of the TCP SYN sent by host 1 to host 2, and this is the encapsulated version of it from Wireshark. The VxLAN technology adds a total of 50 bytes of overhead to the original packet or payload. The VxLAN header itself with the VLAN to VNI mapping is 8 bytes. The UDP header with the destination port of 4789 adds another 8 bytes. The outer IP header containing the source and destination VTEP IPs adds 20 bytes, and the outer Ethernet header, which is rewritten at every hop of the underlay, adds 14 bytes. Now, as per the VxLAN RFC, VTEPs must not fragment VxLAN packets. So this translates to Arista VTEPs setting the do not fragment bit set, as I've highlighted here in red. So we were suspecting possible egress MTU misconfigurations in the underlay from the packet captures on the host, but we needed more data. Generally, pinging with different sized packets and the do not fragment bit set is a good way to check if there are any MTU black holes. I again have the topology set up on the top for reference. So let's start with packet size 1448, because that was the size of the segment sent by host 2 towards host 1, if we recall. So these pings do not seem to be going through. So let's drop the size a bit to 1400 bytes and try this again. All right, that seems to be going well. Let's bump it up a bit to 1430 bytes. That has stalled. Let's drop it again to maybe 1425 bytes. All right, that's going through well. What about 1427 bytes? This seems to have stalled as well. And we can finally drop it to 1426. So we seem to have found our bottleneck, which is 1427 bytes. Now, as you might have already guessed, pinging with size 1427 on this Linux distro does not mean the entire packet size is 1427. This just defines the size of the payload. The ICMP header of 8 bytes is further added. So in truth, the size of the packet that's not going through is 1435 bytes. So this further confirms to us that bigger sized packets are getting affected, and there is an MTU black hole somewhere. How do we confirm what links need to be looked at? What we can do is leave that ping running and trace the path of the packet. So I'm going to continue pinging 10.0.0.1 with the DF bit set. On all VTEPs, there are two monitor sessions configured. One called the underlay, which would mirror packets to and from the spines towards the CPU, and the one called overlay, which would mirror packets to and from the hosts towards the CPU. The spines also have the underlay monitor session set up. Now let's go ahead and confirm if VTEP1 is receiving ICMP requests from host 1, and if VTEPs 2A and 2B are receiving those ICMP requests in the overlay after decapsulation. All right, we see the packets landing on VTEP1, but we do not see them on the overlay on VTEPs 2A and 2B. Now, to further confirm if VTEP1 is encapsulating these packets, we can head over to the spines and take a TCP dump on the underlay monitor session, and we can filter for VxLAN packets by filtering for UDP port 4789. We see the packets here, meaning that the encapsulated packets from VTEP1 are reaching the spines. However, as seen from the packet captures earlier on VTEPs 2A and 2B, we can now see that the spines are unable to route or forward these packets towards VTEPs 2A and 2B. Now, hypothetically, the spines indeed had a lower egress MTU and were hence dropping packets. They would generate ICMP type 3 and code 4 messages back to the source. The source in this case would be the VTEP that's encapsulating the packets, and that's 1111. Code 4 messages indicate that fragmentation was needed, but do not fragment was set. Now we have kernel counters available on our platforms to view the number of such ICMP unreachable messages coming in. The command is show kernel IP counters, and we can filter out the ICMP type 3 or destination unreachable messages that we need. Now the ICMP section that I've highlighted has an input and output histogram. The input histogram had a destination unreachable messages field. So let's do a watch diff on the input messages counter to check if they are incrementing on VTEP1. What I'm doing now is grepping on the input histogram line that we saw earlier. And we're going to monitor the line immediately after that. All right, these seem to be incrementing. Now, of course, we need to see the actual ICMP unreachable message to get more information. So let's go ahead and take a packet capture on leaf 1's underlay and filter for ICMP. It's worth noting here that we should be able to see these ICMP unreachable messages, even if we took a TCP dump on the L3 interface facing the spine, since these messages are intended for this device and would be trapped to CPU. There we go. We see the ICMP unreachable messages. Let's break down one of these packets for a moment. So 10.355 is sending this unreachable message back to 1111. The ICMP message itself says that the spine was unable to reach 2222 and it needed to fragment the packet. It also states that the MTU of the egressing interface is 1500 in this case, and the size of the actual packet that was being routed looks to be 1505 bytes. We also see the original packet's header, which shows that the packet was going towards 2222. We can now hop onto the device with IP 10.355, which we likely know is spine 1, given that we saw the packets landing there. We can see that these 4 interfaces 1/1, 3/1, 9/1, and 11/1 have the default IP MTU 1500. And from LLDP neighbors, we know that these 4 interfaces go towards the 4 VTEPs in our environment. In practice, the underlay is often configured to have an MTU of 9000 bytes or higher to fit jumbo frames without fragmentation, VxLAN or not. We can head over to the VTEPs to check the MTU that they have configured on the spine-facing interfaces. Now, this seems to be 9000 on VTEP 1. Let's go ahead and check the same on VTEPs 2A and 2B. These seem to be the same here as well. So let's go ahead to the spines and set the MTU as 9000 on those VTEP-facing interfaces. We're dropping into config mode and then dropping into the interface-specific mode for those 4 ports. And we're going to go ahead and set the MTU to 9000. And just like that, our ICMP requests with the DF bit set of size 1435 bytes are now going through. Let's also go ahead and check if the kernel IP counters are incrementing now. All right, the ICMP destination unreachables counter has stopped incrementing. Now let's also confirm that the database syncs are indeed going through, which was the original problem statement. Let's run the same secure copy command and punch in the password. All right, the download seems to be going through well now with a higher speed of around 2 Mbps. Now, before we began troubleshooting, it was stated that the SEP was actually working initially, and then it broke. We also discussed that the customer was unsure if any changes were made. On Arista, starting EOS 4.21.3f, we have a command that can show us the historical changes that were made on the device. So let's run the command show AAA accounting logs and grep for the keyword MTU. All right, that seems to be a little noisy. Let's run the command again and grep for the MTU 1500 or just 15 in short. That's a lot better. Let's also run show clock for reference. So we can see here that the current time on both these devices is around 10 a.m. EST. And backtracking a bit, we can see that the MTU was set to 1500 around 7 to 8 hours back by the admin user on both of these devices. This sort of explains the mystery of why this was working earlier and how it could have broken. Presumably, the MTU was set to a higher value on the VTEP-facing interfaces on these 2 spines, and then the admin user came in and for some reason changed the MTU to 1500 on both these spine devices. And therein the problem began. So let's go ahead and summarize the troubleshooting and isolation steps that we took to identify and rectify this problem. We first confirmed that secure copying the file from host 2 to host 1 was indeed failing. We used the SCP utility to do that. And then we confirmed that TCP port 22 was open and listening on host 2. We used the telnet utility to do that. And then we made use of ping with the default size to check if there was connectivity between host 1 and 2. We next got visibility into the traffic sent and received by the hosts via packet captures and observed retransmissions of bigger packets by host 2. We then pinged with different sized packets from host 1 to host 2 with the DF bit set in order to discover any potential MTU bottlenecks. We discovered that ICMP requests of size 1435 and greater failed. We then got visibility into the ICMP requests received by VTEP1. We confirmed that VTEP1 was encapsulating these successfully towards the spine. Spine 1 was not routing these packets towards VTEP2, and the kernel IP counters on VTEP1 showed incrementing destination unreachable ICMP messages. We also got visibility into these actual unreachable messages and accordingly corrected the MTU on both the spines. We finally used AAA accounting logs to confirm that the admin user had actually gone ahead and changed the MTU to 1500 on both the spines a couple of hours back. We've also summarized the commands that we used to troubleshoot and isolate this issue here, and you could use these for reference in the future. So with that, let's dive into problem 2. The customer reported that L3 communication between hosts in different segments was impacted intermittently. They specifically stated that communication between hosts behind VTEP3 to hosts in other subnets was not working at random. Communication within the same VLAN was working reliably, even when the hosts were behind different VTEPs. The topology here is the same. VTEPs 1, 2A, and 2B are routing VTEPs, while VTEP3 is a bridging VTEP. The change here is that instead of using IP address virtual on the SVIs, we've configured IP virtual router address or VARP. The syntax of this setting is slightly different, and each SVI will have two IPs, a physical IP and a virtual IP. An example of a working flow is host 4 to host 1, which are in the same VLAN, VLAN 20, and an example of a non-working flow is host 4 to host 2. The same has been highlighted in the topology in red. Let's head over to the lab now. Using the same Linux hostname utility, we can see host 4 is 20001 and host 3 is 10002. Let's confirm whether pings from host 4 to 10001 are indeed failing intermittently. I'm sending 50 pings from host 4 at an interval of 200 milliseconds. We saw some sequence numbers not going through, and indeed looks like approximately 50% of the pings are lost. I'm also pinging 10002. I'm also pinging the same IP from host 3, which is 10002, and both these IPs are in the same subnet. This seems to be going through successfully. And 0% packet loss, as stated in the problem description. I'm going to next ping 20001 from host 3, and this is the original scenario, as we are pinging an IP in a different subnet from a host behind VTEP3, and we already see some sequence numbers not going through, and there's significant packet loss. The next thing I'm going to do is check how the gateway is resolved on both these hosts. We can see the ARP for 1000254 is resolved to the MAC address 1C73BB on host 3. Similarly, on host 4, the MAC address for the gateway 2000254 is resolved to 1C73BB. As a test, it would be a good idea to now check if this intermittent ping loss affects pings to the gateway. So on both hosts, I'm going to run the same ping command to the respective gateways. I'm pinging 2000254 from host 4 with the same parameters as before. We see the sequence numbers going through. And it's stalled now, and there seems to be some loss. I'm also pinging the gateway 1000254 from host 3. And we already see some sequence numbers being lost. All right, so we seem to be seeing a similar issue with there being a partial loss in the ping packets. This confirms that the issue here is related to the gateway for VLANs 10 and 20 somehow. Now that we've established the problem a bit, let's trace the path of the packet. Let's first confirm that VTIP3 is indeed directly connected to host 3 and 4 via LLDP neighbors. All right. Next, let's verify that this VTEP does not have an SVI for VLANs 10 and 20, since it's a bridging VTEP. All good there. Next, we're checking if the gateway MAC address 1C73BB is present in the MAC address table. It looks to be learnt behind VX1 or VxLAN. Now let's check behind which VTEP this MAC address is present. It looks to be present behind the virtual VTEP or the VVTEP IP 10.10.10.10. And we know that this VVTEP IP is configured on all 3 routing VTEPs. As a next step, we should be checking if all the ICMP requests are actually reaching one of the routing VTEPs, so that it can route from VLAN 20 to VLAN 10. To do that, we can monitor the packets arriving on the overlay on VTEP3 first. The overlay and underlay sessions are configured here as well. So let's take a TCP dump on the overlay session. And we can filter for ICMP. In parallel, we can take a TCP dump on the underlay monitor session of the 3 routing VTEPs. And we're doing this because we don't know where the encapsulated ICMP requests will land. So how we're going to do this TCP dump is by first filtering for the UDP port 4789 because we want to see encapsulated packets. And then we're going to go ahead and splice the contents of the UDP payload because we want to filter for the inner source IP of the ICMP request and the inner destination IP of the ICMP reply. As I've shown in the diagram here, the 4 bytes following the 42nd octet in the UDP payload is the source IP, and similarly, the 4 bytes following the 46th octet in the UDP payload would be the destination IP. 20001 translates to 14001 in hexadecimal. So we're essentially filtering for ICMP requests with source IP 20001 or ICMP replies with destination IP 20001. Now with these captures in place, let's go ahead and start a ping to 10001. All right, so the successful pings are sequence numbers 1, 2, 3, 4, and 13 out of 13 transmitted packets. Let's pivot to VTEP3 first. Remember that we were taking a packet capture on the overlay here. So we're expecting to see unencapsulated packets. Well, we see all 13 packets here, starting from sequence 1 all the way till sequence 13. We can go over to the routing VTEPs now. And we see no packets on VTEP1. On VTEPs 2A and 2B, we do see some encapsulated packets. Let's go ahead and blow up the screen for VTEP 2A. So highlighting the very first packet, we see the outer source IP is 3333, which is the VxLAN loopback on VTEP3. And the outer destination IP is 10.10.10, which is the VVTEP IP as we expected. The inner source IP and destination IP are also expected. And we observe multiple such packets. And upon taking a closer look, we can see all the sequence numbers that we sent out. We sent out 13 packets from the host, and we see sequence numbers 1 to 13 all present in this capture. Now, this confirms that the underlay is working well, and all the ICMP requests are encapsulated by VTEP3 towards 10.10.10.10, and they successfully land on VTEP2A. Now, VTEP2B had also captured some packets, so let's go ahead and check those. These seem to be encapsulated ICMP replies after they are received from the host and routed on this VTEP from VLAN 10 to 20. The sequence numbers 1, 2, 3, 4, 13 are exactly those that succeeded. The outer source IP is 2222, which is the primary loopback IP of VTEPs 2A and 2B. The outer destination IP is 3333, and let's check why this is so. So it looks like host 4's MAC address 7A9 is learned behind the VxLAN port. And let's go ahead and check the VxLAN address table. All right, this host 7A9 is present behind the VTEP 3333. All good here. Now the trouble is we don't know if VTEP 2A only sent some of the ICMP requests towards host 2, or if host 2 actually received all the ICMP requests from VTEP 2A and is failing to respond to all of them. So what we're going to do is take a packet capture on host 2. And since this is a trunk port, we're going to be filtering for VLAN tag 10. We're also going to be initiating TCP dumps on VTEPs 2A and 2B. We'll be using the same filters as before. We'll filter for port 4789, so we see encapsulated packets. And then we filter for the inner source IP of the ICMP request and inner destination IP of the ICMP reply. With that, let's go ahead and start the ping. This time, only sequence numbers 7 and 10 have succeeded out of 10 transmitted ICMP requests. On VTIP 2B, we can again see the encapsulated ICMP replies for sequence 7 and 10 after they are routed from VLAN 10 to 20. And here on host 2, we can see there are exactly 2 ICMP requests that have landed. I'm highlighting these for you. This is sequence number 7 and sequence number 10. So from this, we can conclude that VTIP 2A, despite receiving all the requests, is not forwarding all of them towards the host. So let's go back to VTIP 2A to carefully examine if there's any difference between a working and a non-working ICMP request. I'm going to go ahead and highlight sequence number 6 and 7 here. Both the packets have the same outer source VTIP IP and destination VTIP IP. They also have the same inner source IP and destination IP. However, there looks to be a difference in the inner destination MAC. The unsuccessful request sequence 6 has destination MAC 1C73BB. Whereas the successful request sequence 7 has destination MAC 1C73AA. Sequence 10, the other successful request, also has the same MAC address ending with AA. And the other sequence numbers, similar to 6, all have the destination MAC 1C73BB. So how is this MAC address difference affecting the flows? The inner DMAC should ideally belong to the gateway VTEP so that it can perform routing. Let's go ahead and check the MAC address table here on VTEP 2A to see which of these 2 MAC addresses is owned by this gateway. We'll check the MAC address table for VLAN 20 here. All right. We can see that this VTEP owns the MAC ending with AA, but not the one ending with BB. Hence, it looks like the pings that are succeeding are those that get routed on VTEP 2A, while those that are failing are the requests with an unknown MAC BB, and hence they would be bridged. But why is the host sending requests with varying destination MACs? We are back here on host 4, and we can monitor the ARP for the gateway to check if there are any changes at all. So let's go ahead and run the ARP command for 20.0.0.254. It's the same 1C73BB. Let's go ahead and use the Linux watch utility to check if there are any real-time differences that we're missing. All right. We can see the ARP entry seems to be flapping between the MAC addresses 1C73AA and BB. Now, this explains the different MAC addresses in the packets, but why is the ARP entry for the gateway getting updated at all? A packet capture on the host here may help with that. So we can go ahead and run a TCP dump here and filter for ARP. All right, we see some packets coming in. These seem to be ARP replies. Let's stop this TCP dump for a moment and expand this window just a bit. All right, so we see multiple ARP replies destined to the broadcast address, which is a little odd for the conventional unicast ARP reply. These packets state that the gateway 20.0.0.254 is owned by either 1C73AA or 1C73BB. So it appears that these ARP reply packets are updating the ARP cache on the hosts for their gateways. But that begs the question, who is generating these broadcast ARP replies and why? That can be explained by the fact that we're using VARP or IP virtual router address as a gateway mechanism for this problem. On routing VTEPs 1, 2A, and 2B, the SPIs are configured with 2 addresses, a physical IP and a virtual IP, and this is the expected configuration for VARP. As we can see, the physical IP on each of these SPIs per VTEP is unique, and the virtual IP is the same on all VTEPs per VLAN. Now, one of the key differences between IP address virtual and VARP is that with the latter, the SVIs generate a type of packet called a gratuitous ARP or a GARP. This is done to periodically signal or refresh the gateway binding on the hosts that can potentially learn ARP from such GARP packets. Now I'm running a TCP dump on SVI 20 of all the 3 routing VTEPs so that we can see these GARP packets. As stated earlier, these are broadcast ARP replies that are generated periodically to state that a certain IP, which in this case is the virtual IP, is bound to a certain MAC, which here in this case is the virtual MAC. And since these are broadcast by nature, they would be flooded to all the ports of the VLAN, including all the remote VTEPs. The show VxLAN flood VTEP output displays the flood list programmed on the device per VLAN. So a copy of these GARP packets that we just saw would also be head-end replicated to the remote VTEPs. Now we can head over to the spines to check how these GARP packets look like when they are encapsulated. We can take a TCP dump on the underlay monitor session and filter again for the UDP port 4789. And once again, we can play around with the magic of UDP payload filtering. The 4 bytes following the 11th octet in the UDP payload would typically be the VNI. So let's filter for VxLAN packets with VNI 2020. All right. I'm highlighting the encapsulated GARP packets here so that we can get a sense of how they're reaching the bridging VTEP. The routing VTEPs make use of the VVTEP IP as the outer source IP while encapsulating these GARP packets and flooding them towards all the other VTEPs. Now on spine 1, we see the GARP packets that bind gateway 20.0.0.254 to the MAC address 1C73AA. This packet is destined to 1111, which is routing VTEP1. Let's highlight another packet. All right, so this encapsulated packet, it basically contains the same GARP announcement, and it's headed towards 3333, which is our bridging VTEP. Now it looks like the GARP announcements that bind 20.0.0.254 to the MAC address 1C73BB are being hashed to spine 2. Like in the previous case, the GARPs are flooded to the appropriate VTEPs in the flood list. We can see one copy going towards 2222, which is the routing VTEP 2A2B. And here we see another copy headed towards our bridging VTEP 3333. Now, I've captured these very same packets in a PCAP file so that we can see them in Wireshark. So let's head over there. These are the very same packets that we saw just a moment back. Let's go ahead and check the outer IP header first. We can see the outer source IP is 10.10.10.10, which is the VVTEP IP used by the routing VTEP when it encapsulates the GARP packet and head-end replicates it. The destination VTEP could be any IP in its flood list. From the VxLAN header, we can see that the VNI is 2020, meaning this GARP packet was generated by SVI 20 of one of the routing VTEPs. From the inner Ethernet header, we can see the destination MAC address is the broadcast address, all Fs, and this is a characteristic of the GARP or gratuitous ARP. And furthermore, in the ARP payload, we can see that the opcode is 2, indicating that this GARP packet is an ARP reply. And we can see the sender MAC and the target MAC are the same, which is the virtual MAC 1C73BB. And the sender IP and target IP is also the same, the virtual IP. So why are we seeing contradictory GARP announcements for the gateway IP 20.0.0.254? To better understand this, we have a very useful command that we can run when VARP is the chosen Anycast gateway mechanism. This is show IP virtual router with a VRF context, VRF-A here. Now this output is helpful because we can see all the active gateways and their IPs for a specific VRF. Furthermore, we can also see the configured gateway MAC address. Now there seems to be a very clear mismatch in the configured gateway MACs. The virtual MAC on VTEP1 is 1C73BB, whereas on VTEPs 2A and 2B, it's 1C73AA. Now, this would cause the guard packets to be generated on each of these SPIs with that respective MAC address. Now, this explains why only certain ICMP requests were being forwarded to host 2 from VTEP2A, while others were being dropped. The requests with the inner destination MAC as 1C73AA were getting successfully routed towards host 2 because VTEP2A owns that MAC address. But for packets coming in with the inner destination MAC as 1C73BB, VTEP2A would try to bridge that packet since it doesn't own that MAC address. Now we know that 1C73BB from this output is actually present on VTEP1. And to reach this, VTEP2A would have to send this packet back out of the VxLAN port. But just like all L2 forwarding, there are strict split horizon rules with VxLAN as well. Since that packet landed on VTEP2A over VxLAN, it would not be sent back out of the same port. Hence, traffic with the inner destination MAC as 1C73BB would get blackholed on VTEP2A. So to go ahead and rectify this, we can configure the same virtual MAC across all 3 of these routing VTEPs. Let's first check how the virtual MAC is configured. All right, the command seems to be IP virtual router MAC address and then the address. So let's configure 1C73AA to be the common virtual MAC across all 3 of these routing VTEPs. We can again run show IP virtual router to see if that change has taken effect. And it looks to have taken effect. We can see 1C73AA is the IP virtual router MAC. With that, let's go back to host 4 and check if our pings are succeeding. We're again sending 50 pings at an interval of 200 milliseconds. Great, 0% packet loss finally. Let's again perform the same exercise and now take a packet capture on VTEPs 1, 2A, and 2B with the same filtering as we did before. 10 packets this time. All right, so on VTEP2A, we see all the ICMP requests have hashed, and we can clearly see that the inner destination MAC is 1C73AA across all the packets. And on VTEP2B, now because VTEP2A would have forwarded all of those ICMP requests towards the host, we see all the ICMP replies land here successfully. Now with that, let's go ahead and summarize the isolation and troubleshooting steps that we performed here. The first thing that we did was to confirm that the ping between host 4 to host 2 is actually failing intermittently. And then we went ahead and pinged the gateway of host 4, and that was also failing intermittently. As a sanity check, we pinged from host 3, which was behind the same bridging VTEP3, to host 2, which was within the same segment as host 3, and that ping succeeded. We used the failing ping between host 4 and host 2 as our source of truth, and we traced the path of the packets, and then confirmed that VTEP3 was encapsulating all the ICMP requests to VTEP 10, 10, 10, 10, which is the virtual VTEP IP. Now, these packets could have landed on any of the 3 routing VTEPs. So via a packet capture, we confirmed that they were landing on VTEP2A. Next, we confirmed that VTEP2A was receiving 2 kinds of ICMP requests. Some of them had the inner destination MAC as 1C73BB, and the others had the inner destination MAC 1C73AA. We further saw that VTEP2A was only routing packets with the inner destination MAC as 1C73AA, and we soon found out that that was because it owned that MAC address in the form of the virtual MAC. We then backtracked to the host, and we confirmed that the ARP for the gateway 20.0.0.254 was flapping between 1C73AA and BB. This was because host 4 was receiving GAR packets that had contradictory announcements for the gateway IP. Now, the routing VTEPs had VARP configured as the gateway mechanism, and they had different virtual MAC addresses configured across them. So we went ahead and identified one MAC and configured a uniform virtual MAC across all of them, and then the ping loss ceased. We have summarized the list of commands that we used to troubleshoot this issue down here below. And more importantly, beneath the topology diagram, we have a list of all the VxLAN filters that we used in this problem. The highlight here is the UDP splicing that we've used to focus on the VNI, as well as the source IP of the ICMP request and the destination IP of the ICMP reply. You can play around with these for your own troubleshooting. And with that, we would have some key takeaways from both of these problems. It's always good to first establish the problem description by performing a few connectivity tests, as well as running some validation show commands on the CLI. Packet captures are your best friend. So depending upon the scenario, try to validate your theoretical packet flow with actual packet captures at the control or data plane level. Of course, reviewing documentation is also a must, especially when one wishes to adhere to best practices. For instance, in this case in problem 2, if one had reviewed documentation, they would know that the virtual MAC that has to be configured across the routing VTEPs within a specific VxLAN environment would need to be the same. Now, while choosing the Anycast gateway mechanism for VxLAN, there are some caveats with both methods, with both IP address virtual as well as with VARP. With IP address virtual, the pings to the hosts, either local or remote from the gateway, may not always work due to the source NAT that we talked about. And extra configurations may be needed either on the hosts or the VTEPs to make this work. Now, if you have VARP configured, one may have hosts in their environment that would be enabled to learn ARP for their gateways from the GARP packets that are generated by the SPIs on the routing VTEPs. That would have to be kept in mind while designing the environment. And with that, we've come to an end to the troubleshooting section from the command line perspective. I'm going to hand this over now to my colleague Vijay to walk you through the cloud vision aspect of troubleshooting the first problem that we discussed. Over to you, Vijay.
Thank you, Sandhya. Good morning, everyone, and welcome once again to the webinar session 6. My name is Vijay Gopal Sriram, and I'm a technical solutions engineer at Arista Networks here on the West Coast. Today, we will be looking at the debugging traffic flows in a VxLAN routing environment using Cloud Vision. We will be referencing problem statement 1 from the CLI demo and go over how to troubleshoot it end-to-end using Cloud Vision. Let's do a quick callback to the problem where the customer reported that file transfer using SCP isn't working across the VxLAN fabric. So the flow is set between host 1 and 2, where a file that is residing on host 2 needs to be transferred to host 1. Now, based on the initial troubleshooting from the customer, there were some tests that were performed and some additional details were shared, as we see on the screen. So the issue was reported initially on June 19th, around 10 a.m. Pacific time. The file transfer stopped working recently, and the IP reachability between the end host seems to be working fine, with ping tests to be confirming the same. However, there was one interesting point that was also shared, where the pings with regular size packet sizes were working fine, but then stopped working as and when we bumped up the packet size. So the scope of today's session would be to leverage the following functionalities in Cloud Vision to debug the flow, namely topologies, events, device telemetry, compliance overview, and config comparison. With that, let's head over to the Cloud Vision UI to start debugging the flow. We are right here on the topology page where we see a logical connectivity between the devices. We have spines and the VTEPs here. To begin with, let's verify if there are any L1 discrepancies in the system. To do that, the topology view gives a functionality using the overlay color coding scheme. On the left-hand side, in the overlay drop-down list box, let's scroll down until we see the operational status option. Clicking on that gives us a bird's eye view of L1 states across the devices in the fabric. Now we can see the color coding scheme from the legends on the right-hand side. And based on that, we can verify that the links are healthy between spines and VTEPs and also the hosts. Now, let's go ahead and look into the flows to visualize the traffic path. Now on flows, we can see some TCP and UDP flows on the left side that are ongoing at the current time. However, we are more interested in the ICMP flow based on the test. Hence, I'm going to filter out using the protocol ICMP from the list. Select ICMP and then hit done. Right now, we don't see any traffic flows at the current time. On the top right-hand side, we see a timeline box that says 30 seconds with a green highlight. Clicking on that brings up the timeline bar at the bottom. Now we see that we are in the live mode. Remember that the issue was initially reported on June 19th, and following that, there were some ping tests that were performed. Now, one of CloudVision's biggest strength is to go back to a particular time in history and view the states at that point in time. Now, we are going to leverage the same functionality by going back to the specific time when these ping tests were performed. And we are going to visualize the traffic flows there. So let's head over to the time range window option on the left-hand side bottom. Clicking on that brings us the calendar and the clock. Now, the calendar set for June 19th. And as per the details shared, the first ping test that was for the working flow was performed at 10:04:50. So I'm going to go ahead and set the clock to the exact time, 10:04:50, so that we can view the states at that point in time. Now, there is also an option to set the window, which I'm going to set for 1 minute. Now, after setting that, let's hit apply. Now we can see two different flows on the left-hand side, 10:001 to 20:002, and the other one, 20:002 to 10:001. To get more details on these flows, let's go ahead and inspect them one by one. Now I'm going to start with 20:002 to 10:001. Clicking on that. Now this gives us flow animation where we can see packets going from host 1 towards host 2. On the left-hand side, we can see all the flow-related details starting from the source host, destination host, which is like host 1 and host 2. And then there are devices that report matching flows. And these seems to be consisting of VTUP1, Spine1, and VTUP2A. You can see these are the devices in the traffic path. Let's head back to the flows and take a look at the reverse flow, which is 10:001 to 20:002. Now clicking on that again. Now here we can see this is the reverse traffic as the source and destination IPs have been reversed and the packets are being sent from host 2 towards host 1. The devices that match this flow seem to be the same as the traffic has taken the same path in the reverse flow as well. Now let's jump back to the next timeline where the customer reported that the ping tests were breaking when the packet size was bumped up to 1427 bytes or even higher. So this test was performed at 10:09:50. I'm using the timeline window again to set the clock to 10:09:50, retaining the same window of 1 minute. Now clicking on this, we see two different flows. The first one seems to be familiar, which is 20:002 to 10:001, which we saw in the previous scenario, host 1 to host 2. Now there is another flow which doesn't look to be the reverse flow, and we need to investigate what this is. Let's first take a look at the known flow and see if there are any differences between the scenarios. I'm clicking on that. Here we can see the source is host 1, destination is host 2. The protocol is set to ICMP as per the filters that we set earlier. But there is one difference where the devices that report this matching flows are only VTUP1 and Spine1. We do not see VTUP2A. And this looks like the packets are also not making its way to host 2. To understand more, let's look at the other flow, which is the new one in this scenario. Now clicking on that, here we can see that there is only an unidirectional traffic between Spine1 and VTUP1. The source looks to be of Spine1 and the destination is that of VTUP1. Protocol is still ICMP, but the only device that matches this flow looks to be of VTUP1. Now this is a traffic coming from Spine1 to VTUP1 and looks like Spine1 is not forwarding the ICMP traffic that it got from VTUP1. Now to understand more on what these ICMP messages are, we could leverage the TCP dump on the switches as shown in the CLI demo. Now that we've verified the flows, it also makes sense to understand if there were any events triggered as a result of network change. So to do that, we can leverage the active events functionality from the topology page, clicking on the topology settings and enabling the option that says show active events. Once we enable that, if there are any events on any devices, that would show up. Here we can see on spines 1 and 2, we have a small icon popping up. Hovering the mouse over that will give you what kind of an event is that. Here it seems to be that of a warning event. Now to get a glimpse of what these events are, let's go ahead and click on one of the devices, say spine 1. And on the left-hand side, let's navigate to the active events tab. So here we can see spine 1 says device is out of config compliance. Let's verify the same status for spine 2 as well. I'm going back and clicking on spine 2. Heading back to the active events, we still see spine 2 is also reporting a config compliance event. Now this indicates a potential config change somewhere in the system. Now that we have viewed the device-specific events, let's also make sure if there are any link-related events, such as interface errors or discards. To do that, we have the same functionality from the topology page by leveraging the overlay color coding scheme. Going back to the main topology page, click on the overlay drop-down list box and scroll all the way up until you see active events. Clicking on that would immediately highlight all the links if there are any events. Here we can see that all the links between spines and the VTEPs are being highlighted. Based on the legends, we can see that these links are having an active critical event. And hovering the mouse over any of these links would also indicate what type of an event is that, similar to how we saw for the warning. Now to get a glimpse of what these events are, let's go ahead and click on one of these links, say between spine 1 and VTEP 1. Now, clicking on this link brings up the physical topology connection where Ethernet 49/1 on VTEP 1 is connected to Ethernet 1/1 on spine 1. Let's head over to the active events tab. Here we can see spine 1 Ethernet 1/1 is having an interface MTU violation. And this event seems to have started on June 19th at 9:30:52 Pacific time. To get more details on what this event is all about, we can click on this quick description that would directly take us to the main events page. Let's go ahead and click on this event to head over to the events page. Here the event title says interface MTU violation on Ethernet 1/1 on spine 1. A quick bonus tip here, we have a small info icon and hovering the mouse over that gives us the quick link to the event configuration guide on the community portal. And this would take you directly to the particular category, which in this case here is interface MTU violation. Going back again, we see that this event started on June 19th at 9:30:52. Note that at the bottom on the timeline bar, we see that we are still on the time when this event actually started. This is an important point to note that whenever you are inside an event, you are not on the live mode, but at the time where the event started. Going back to the description, it says that the interface MTU value, which is 1500 bytes, is less than 1600, which was configured by the user. Now on this page, we also have a whole lot of interface details. We have the interface config with a description that says it is towards VTEP 1. Looks to be an underlay port between spine and VTEP. From the interface status graphs, we can see that this port has been admin enabled and has been in the connected state around the time of issue, which is good. And we also have the graphs for counters, traffic rates, and errors. We see that there are no error counters in both inbound and outbound direction. We do see some active traffic when the test was performed. All right. So to get more info on the rules of how this event was configured, we could go over to the event generation page, which can be right accessed from this one. Clicking on the configure event generation would take you directly into the event config page. Here the category is interface MTU violation. You also have the quick link to the event config guide from this page as well. So this event has a custom rule number 1, that has some active devices queried using the container tags. And these seems to be of leaves and spine containers. We have 6 matching devices, and clicking on that will populate the list of actual devices that have been queried. Below that, we have the interfaces section, where quite a few interfaces have been queried using the description tag. And there are a total of 16 interfaces consisting of the spines and VTIPs. It's always a good practice to label all the interfaces, which would be helpful for a user to give some meaning, and also will be helpful to tag the interfaces on CloudVision for events and topologies. Now we have the checkbox that says generate an event, which has been enabled, which is obviously going to generate an event when the conditions are met. The severity is set to be critical, and the threshold is set to 1600 bytes. So this custom rule would generate an event if the interfaces queried above, if any of them would have an MTU that falls below 1600 bytes. And heading back to the events, let's just make a note of the start time, which would be critical in determining if there were any changes in the system around this time. Now we can go to the devices tab or use the quick link from this page to directly head to the devices. I'm going to click on Ethernet 1/1, which takes me directly to this interface. Here we can see the MTU is set to 1500, which directly correlates the event that got triggered. We can confirm the description is towards VTIP 1. And at the bottom, we can see the timeline is around 9:32, and we are not in the live mode. We are in the historical timeline mode. To understand if the other underlay ports on the spine is also having this issue, let's click on interfaces and go back to the Ethernet section. We have all the ports listed here for spine 1. However, we want to look at only the underlay ports. Hence, I'm filtering for the description with VTIP. Now, this lists only 4 interfaces, namely Ethernet 1/1 to 11/1. And on the right side, we can see the MTU for all these ports are set to 1500 bytes. Now, the default MTU is always 1500 bytes on any Arista device for a routed port or an SVI. And note that we are still in the time in the history when this event started. As per the rules, since the event got triggered as the threshold fell below 1600, the MTU should have been higher earlier. To understand if there were any config changes made, let's head over to the configuration section to view the changes. Let's scroll up where we can see configuration. Clicking on that gives us the config page. And on the right side, we have the change history. I'm going to take a look at the most recent change at 9:31. Now, clicking on that gives us the running config for spine 1 comparison between 2 different timelines. The first one is 9:31:04, which is the current time when it was changed, and the other time was 9:27:14, which was before the event got triggered. On the left side at 9:31, which was after the event got triggered, we see that all the ports do not have any MTU values, whereas they had the MTU set to 9000 explicitly before the event got triggered. Now, this not only indicates a change in the config, but this also indicates that the changes might not have been done from CloudVision. To understand if the spine is still having the same config, we can click on the timeline bar and select the use current time option, which would give the comparison of spine 1 at current time against the time in history. Now we can very well see that spine 1 running config doesn't have the MTU values for any of these ports, which was present before the event got triggered, which indicates there was a change in the running config. Note that we had a device config out of compliance event on the topology page. Now that also indicated a config change. To get more details on that, let's leverage the compliance overview functionality by heading back to the devices and selecting compliance overview. Go back to devices and click on compliance overview. Here we can see that spines 1 and 2 are reporting config out of sync. Now again, the timeline at the bottom says 9:27:14, which was on the second change timeline before the event got triggered. To get more information on these, let's go ahead and click on one of the status, say for instance, spine 1. Here we can see a comparison between the design configuration and the running configuration. On the left-hand side, where the design config is populated, we can see all the ports that are going to the VTEPs have an MTU value of 9000 set explicitly. On the running config, with the right-hand side, we don't see these values. Now again, this not only indicates that there was a change in the configuration at some point in time, but also shows that the change was not done from CloudVision, perhaps from CLI. To substantiate that, we can also look at the design config source. But before we do that, let's verify the changes on spine 2 as well by clicking on the spine 2 status. Let's close this dialog box and head over to spine 2 status. We can see that spine 2 is also reporting a similar change as that of spine 1, where the MTU values that were set in the design config is not present in the running configuration. To understand where the design configuration is being retrieved from, let's click on the device, say spine 1, which takes us to the config page. And here we can see there is a configlet named spine1 _ serial number. Filtering out by the MTU, we can see there are 4 results. And clicking on one of them would directly take us to the actual config in the design configuration. We see that MTU value 9000 is set to Ethernet 11/1. Let's verify the same for spine 2 as well. You can see the search filter is already set, and clicking on one of the lines shows us that the MTU values are set to 9000 in the design configuration. Now, this once again proves that the design configuration was not touched, but the running config was changed. We have a very clear root cause of why the file transfers stopped working suddenly, and these data points that we gathered from the CloudVision telemetry so far complements the same. The recent change to the running config with the removal of MTU has resulted in the file transfer issue. The changes can be verified using AAA accounting logs from the switches, as we observed from the CLI session. At this point, let's also do a quick recall for the need for a higher MTU in a VxLAN fabric. The MTU needs to be set in a way to accommodate the additional overhead of 50 bytes for the VxLAN header. It's a good practice to set the MTU on core links to 9000 so that the jumbo frames are not fragmented. As we figured out the issue, let's go ahead and fix that by making the changes, pushing into the running config. If I click on one of the switches, we see that we have the spine 1 config applied. Clicking on validate populates the design and running config comparison. And we have 4 new lines, which are essentially the MTU related configs. Once we verify those, we can hit save. And then clicking on save again would create a task. Now we can perform the same steps for spine 2 as well, which would then create a task, and we can bundle these tasks into a change control. And then we would be able to execute that. Now, in the interest of time, I'm going to do that in the backend. And during that time, let's take a quick look at the topology page, where we see that the events are still active with the link and the device-specific events. Let's just give it a few seconds before the change control can actually complete. And once we do that, we can go ahead and verify the topology page again. Let's head back to change control. You can see that the change control has completed successfully. And from spines 1 and 2, we can see that there are 4 new lines that have been pushed into the running config. Now it's time to go back to the topology view to see the changes. Let's go back. And here we can see that the link specific events and device specific events are no longer visible. We can still see that the settings for show active events is still enabled on the topology page. As a final verification step, let's perform an ICMP flow between host 1 and 2, but with a higher packet size than earlier. Let's head back to the flows. Let's filter out with ICMP as before. And this time we are going to perform a ping with 1450 bytes. And there are two flows, and taking a quick look at both the flows, you can see the circuit is completing between host 1 and host 2 for the forward. And similarly, on the reverse flow, you can see the packets are going between host 2 and host 1. That would be the end of debug flow. Let's take a quick recap of the steps done so far. To summarize, Cloud Vision offers advanced techniques to complement traditional network troubleshooting. The real-time telemetry combined with the historical timeline view is one of the biggest strengths of Cloud Vision. The ability to go back to a specific time in history proves helpful in root cause analysis. Right from flows to events and configs, this timeline feature played a very important role in debugging its flow. The topology view not only helps us visualize traffic flows, but also provides functionality to identify active events, layer 1 states across devices. These features actually gave us a kickstart in troubleshooting this flow. Finally, the events and compliance overview plays a very critical role in identifying the changes in the fabric. It lets us stay tuned of all the ongoing changes in the environment and can help minimize or even avoid a potential impact. Now that brings us to the end of Cloud Vision part. Here are some useful references of all the features that we touched upon in today's session. Thank you, everyone. Over to you, Lokesh.
Thank you, Vijay. Yeah, let's perfect. So thank you, Sandhya, and thank you, Vijay, for the outstanding delivery. It was indeed a comprehensive deep dive on VxLAN, and it's truly been a technical treat for all of us. So for our customers, we sincerely hope that you found this session incredibly valuable. Again, the recording of this session will be available on the Arista community page, along with the presentation material and the questions what we have covered as course of this presentation. Just a reminder on the webinar schedule, which is coming in Q3 for EVPN series. We have 3 sessions scheduled, and our next session is going to be on August 30th at 11 a.m. US Eastern, and it's going to be an introduction of the EVPN. In the course of these 3 sessions, what we have, we'll be doing a very complex, like we'll be covering a complex scenarios in the EVPN, and we'll do a comprehensive deep dive in the EVPN as well. The series will go from August to October, and it'll be we are actually taking a gap in July, and then we are resuming in August for the EVPN session. So we highly encourage and recommend everyone to attend our EVPN series, where we are going to cover a lot of good practical use cases in that. In order to continually improve and cater to your needs, we have a feedback form available, and we kindly request your participation in that. The form link is shared in the chat, and it has, I think, 3 to 4 questions. So your feedback is immensely valuable, and we'll incorporate these feedbacks in our future sessions, which are coming in Q3. So with that, I'm going to keep the webinar open now to answer any questions what you may have. You can use the Q&A manager to ask our panelists any questions at this point. Okay, so I think there's just one question which is open in the Q&A, and I think our leads are actually typing the answer to that. So after that, if there are no other questions, then we are going to wrap it up. Thank you, everyone, for joining us today. We really appreciate your time, and hope you enjoyed this session as much as we enjoyed putting this together for you. Thank you again, and have a wonderful day ahead.